Hi, I'm Scott McDonald. I'm an application engineer with Siemens SimCenter Test Products, and we're going to talk about making some simple measurements in SimCenter Test Lab today. And so as an agenda here, we'll go over a brief introduction, kind of what I was thinking when we came up with this webinar idea. We'll review some of the equipment that you use to take a simple measurement. And then the meat and potatoes of this presentation is really going to be about acquiring time data and the simplest, easiest, fastest way to get to acquiring high quality time data, because everything in noise and vibration stems from that time data, be it sound quality, listening, jury testing, all the way to modal analysis or other vibration work. It all hinges on having good time data. So what I'm going to do is show you the fastest, easiest, quickest way to get reliable time data. And then afterwards, we'll talk a little bit about some specialty frequency-based information like computing loudness versus time, or overall sound pressure level maybe. And then lastly, we'll talk about doing a quick resonant frequency test. So imagine I want to check the bending mode of 100 steering columns, and I need just a real quick impact test to do that. I'm going to show you how to set up that test template as well. Now, in order to take any data with SimCenter Test Lab, we're going to need some data acquisition hardware. That is, of course, the SCADIS hardware. And in this case, we have primarily two flavors of the SCADIS hardware. The SCADIS XS, which is the smaller handheld unit on the left there, and then the SCADIS Mobile family, which comes in various sizes depending on your channel count requirements and things, but it's all basically this same sort of chassis design. And again, we're focusing on what I'm calling grab and go measurements here today. So at the last minute, you find out you've got an hour to take some critical data on maybe an experimental vehicle that you're not going to have access to, or some other last minute data acquisition campaign. So you don't have time to prepare. So this is truly, I need to grab something and go take some data. That's the kind of case we're going to look at today. And these are the two kinds of SCADIS that you can use for that application. There's also a lab-based system called the SCADIS Lab. Can't really take that out of the building, so it's going to be a little bit different scenario. So we're going to focus on these two today. And if you're working with a SCADIS Mobile, you are going to need a computer, a laptop with SimCenter Test Lab on it, and you're going to need a LAN cable, an Ethernet cable, to connect that front end to your laptop. Again, there are recorder frames in the mobile suite, but those you have to set up ahead of time. For today's discussion, we don't have time to set up a recorder template, so it's either a laptop or bust with Test Lab. And then if you have the XS, you can do the same thing. So you've got your laptop anyway, you hook it up to a USB cable, and you can run SimCenter Test Lab and start your test from scratch using SimCenter Test Lab, no problem. The nice thing about the XS is it also has the functionality to work wirelessly with a Wi-Fi tablet, and it has its own dedicated software called the SimCenter Test Lab Scope app, and we'll take a look at that as well. So those are our two main hardware options in terms of grabbing and going. So now we're going to talk about acquiring time data. Okay, now it all really comes down to getting time data, because everything else you do in terms of noise and vibration analysis can be done in post-processing, provided you have this time data. Okay, and what is time data, or throughput data we sometimes call it? It's high-speed, digitally sampled data. It's a tape recording, if you will, of everything that those transducers, the microphones, the accelerometers, the strain gauges, everything those transducers are seeing gets digitized, and it's a recording of everything that happens. Okay, And so it's really the starting point for any kind of measurement or analysis. It can be used for direct playback or listening. If you're recording acoustic data with microphones, or even better yet, a binaural headset, you can play back that data directly and use it for a jury test for a sound quality analysis or something like that. Or you can feed it into SimCenter Test Lab, and all of that time data can be post-processed after the fact and get all kinds of other information like frequency data, frequency spectrums, order cuts, waterfall plots or color maps, overall sound pressure level versus time, things like that. FRF for modal analysis, all can be extracted from time data. So we're going to focus on acquiring high quality time data today. Okay. Again, we need to grab and go with last minute data acquisition campaign. Okay. So what we'll be focusing on today will just be the bare minimum I need to get that time data. Okay. We're looking for the fastest setup, the least experience needed. So maybe I take data once a year, or I'm a manager and I don't take data at all. If I have some of the tricks we're going to learn and I'm going to show you today, you can do this and you can get your time data. Okay, and the end result is we're going to have a basic measurement template, a thing we can open that is going to have all of the settings and everything done for us. Okay. When I was working, I had a 3.5-inch floppy diskette that fit into an HP 4-channel analyzer, and when I had to take data at the last minute, I grabbed that diskette and I would put it in that HP analyzer, and I could use it to set up the test very quickly, and it was a lifesaver for me. And so that was really the genesis of this idea for this webinar. So hopefully I can give you the modern day version of that 3.5-inch life-saving floppy disk. Okay. Now we are making some assumptions. Obviously, I'm assuming you have access to some transducers that you're familiar with. Ideally, these are yours. Maybe a little kit that you have where you have a microphone or a couple microphones and some accelerometers that you use over and over. And so the sensitivities and the serial numbers and things would remain constant. It's an assumption, but it's not that unlikely. Worst case, you have a slightly incorrect sensitivity that you use using some of these techniques, but all of that can be fixed after the fact. We're also assuming that we don't need to calibrate. We're going to use some base factory sensitivities for these transducers, so our amplitudes will not be super accurate necessarily. Okay, if you need to do super accurate testing, some of these techniques are not going to work for you, or you'll need to supplement them with a calibration step. Okay, you should always be calibrating if you're really interested in getting the highly accurate amplitude measurement. Okay, we're skipping all that today. We just need some time data, and we need to be able to get it at the last minute. Okay. So our first software we're going to look at is this SimCenter Test Lab Scope app. And this is the software that runs on the wireless tablet that can come with your Scatus XS system. Okay. One of the nice things about the XS is that it also has a direct built-in input or a plug on there for this binaural headset. So we sell this headset. It's got microphones at the ear positions, and the benefit of making a binaural recording is that you're recording at both ear positions, and so you get a very, very lifelike, realistic audio recording. It sounds way more convincing than just a single microphone. Okay, if you've ever listened to a single microphone recording, it sounds similar to what you may hear standing there, but it's not identical and it's not very similar. The binaural headset will really give you that lifelike quality and capture some of the effects of you standing in the acoustic environment. That's why a binaural recording is almost always used for sound quality jury testing. If you're listening in headphones or even in a loudspeaker playback, they'll be using a binaural recording because it captures the lifelike 3D effect of the sound. Okay. And so we can use this binaural recording directly, or the headset directly with the XS. We can make this binaural recording. Of course, we can plug in a bunch of accelerometers or microphones as well. But the nice thing about the XS with the headset is that the equalization is built right in. We can do it automatically with the software and the hardware. So whether we're going to be doing calculations of sound quality metrics on the data or we just want to play it back, we can work that equalization directly with the hardware and the headset. So it's truly a grab and go solution for anything from sound quality all the way to, basic noise and vibration processing. Okay. So let's take a look at that tablet software. This is a screen mirror. I'll maximize this. So this is a screen mirror of the tablet that I have hooked up to my XS and to my tablet or to my computer. And you see this TestLab Scope application. So I'm going to launch that. And it's now communicating with the XS. It's going to boot up the software. And I'll show you how to set up a template from scratch here. Okay. So the first thing you see is you have a list of what we call templates, and these are pre-made or test setups that we can use and make our own. And all we have to do is select one and hit that measure button, and we are off and running. Okay, so this is where we're going to create a brand new template from scratch, and that we'll have at our disposal. We keep it on our tablet, and anytime we have an XS and this tablet with us, we will have this little 3.5-inch floppy emergency use template. Okay, so in this case, we're going to say new here, and we're going to create a brand new one from scratch. Okay, and so this first tab, you see we have all these tabs across here. We're going to step through these as we set up the template. But really what we have here on the left is a list of the channels, and this is a 12-channel unit, and so I've got 12 channels plus the headset plus this binaural digital input that I can use for a secondary head measurement system. In this case, I'm going to turn the headset on, and this is pretty much set up already because it's a dedicated input only used with this headset. Okay, I can come in here and I can type maybe a user ID. It's already set up in the acoustic group, the sensitivity is already there, and this is where I can do the equalization for analysis. So it's going to remove the head and torso effect automatically for me, and it will reapply that when I use it to play back the recordings. All right, similarly I can come over here and say this is the right headset, and then I'm going to come down here and I'm also going to have a 1/2-inch microphone. Okay, and so channel 1A is turned on. If I wanted to turn more on, I would just click on them. In this case, I'm just going to turn one on, and I'm going to call this just mic. And we're going to measure, instead of acceleration, I'm going to measure pressure. The two most frequently used are put right here at the top of the list for me, but if I needed to measure temperature or something, I can just start typing and it'll find it for me. In this case, I'm going to be measuring pressure. And I'm going to turn on ICP down here, and it is an ICP transducer, and so that allows me to use this read TEDS. Okay, so I'm going to read the TEDS transducer. The headset's also plugged in. Those are also TEDS, and so you see it automatically pulled over the sensitivity for my headset and this microphone. It's going to import those for me, and I am set up. Okay, I've got a headset plus a microphone, and my channels are set up. Okay, if I wanted to calibrate, there's also a calibration part here. We're going to skip that for now and just use this default sensitivity for the microphone. Okay, I'm not going to use a tacho today. I'm just going to be measuring raw time data, so I'm not going to worry about that. I also could plug in the GPS antenna. I'm going to skip all that today. CAN bus as well, and I'm just going to go to this measurement tab. And I'm going to leave this basically as is in terms of a start trigger. I want it free run. I just want to be able to start when I hit record, and I want it to record like that until I hit stop. Okay, the most general, flexible way I can do that is just manual start and stop, and don't time out or anything in between. In this case, I just want to also make sure that my sample rate is maxed out, right? I don't know what kind of frequency range I might be interested in, so I'm way better off sampling too fast than too slow. If I only sample at 2000 hertz, my frequency bandwidth when I go to calculate an FFT is only going to be 1,000 hertz wide, right? And so if I'm interested in acoustic information, that's going to backfire on me. And so I'm better off setting up this generic time acquisition as being wide open. Okay, so I'll set the acoustic group to 51 kilohertz, which is the maximum sample rate for the Scatus XS. Just to double check, I'll try to set the vibration group up there as well, just in case I've screwed something up. Oops. Up here at 51.2. And now everything is set wide open to acoustic and vibration 51 kilohertz. Okay. So now I'm ready to go. I'm going to do one more thing just because it's kind of a neat feature that's come relatively recently. I have this tablet with me, right, in my Scatus XS setup. We now allow you to record the feed from that camera live. You have the tablet with you, might as well get a recording, a video recording of your test. So you see this is a live video feed of the tablet sitting on my desk here. And it's just a nice thing to have. It might capture something you don't anticipate. So I always put it on. You can also turn on the rear camera as well. Okay, I'm going to save that, and we'll call this time data. Headset 1 mic. Okay, and so now in this list of templates, you see I have this template called time data headset 1 mic. And I get a summary of that setup over here. It's one channel plus a headset plus a camera. And it's free run to start and stop. Okay. And so now I am ready to go anytime some last minute data acquisition emergency situation comes up. I can grab my XS, use this template, and I'll be able to go to acquire some time data. So let's see what that looks like with the XS real quick. And we'll take a look at some of these different views here. We have the base view, which is just a big flashing start and stop button. If I were to touch the screen here, it'll start recording, and it's recording everything. It's recording the left and right headset plus the microphone as well as my camera over here. Okay, and it's just a big, nice, easy to hit start and stop button. In this case, I'm going to delete that run because I don't really need it. And then I can also look at some of these other views. Analog is really for an RPM thing. This is a digital. I just want an overall dB value from all of my microphones. We see that they're all relatively similar, which makes sense, right? We're just listening to me talking right now. You can also look at a strip chart display. And here we will see the left and right headphones. We get some squiggly lines. Maybe we do some clapping. It gives us a good warm fuzzy that we are ready and to take this data, and we'll see live data coming in. It's not noise or a bad cable or something. There's also a statistics view, which will show you a min, max, our mean, that sort of thing. And then the functions is where we can look at a live spectrum. Okay, so in this case, I'm seeing a live 1/3 octave spectrum. If I come up here, I can also change that to maybe a narrowband FFT, which is what we see here. I can also see things like total loudness. So this is loudness in sounds, a sound quality metric for the perception of loudness versus time. Okay, so really, really nice if that's what I want to look at. I also have sound pressure level. Okay, so this is just an 8-weighted LAF sound pressure level versus time, and I'm ready to rock. All of this can be seen right here on the tablet. Okay, so super fast and easy. Now I'm going to back out of that because I don't really need to take this data, and I'll back out twice here, and that's the tablet application. Okay, so SimCenter Test Lab Scope app with the Scatus XS, boom, check. I've already got a time data acquisition template all set up. Now let's jump back over to the presentation and take a look at another option if maybe we either have an XS or we have a Scatus Mobile. I'm going to show you some similar functionality in SimCenter TestLab Neo, which is the new user interface for SimCenter TestLab. So I'll show you the simplest, easiest way to do the same exact thing I just did on the tablet application in TestLab Neo. Okay? Close this for now. Okay, so now I'm going to show you the same sort of process using SimCenter TestLab Neo. Now the Neo product is sort of the new user interface and the sort of the future look of TestLab, SimCenter TestLab. And so we obviously want to go into the general acquisition folder here because we want to acquire time data. Okay. In this case, the nice thing about Neo is that the product is named exactly what we want to do, which is time data acquisition. Okay. So I'm going to launch that. And it's going to start talking to my front end, and I'll be met with this. Do I want to open an existing template, or do I want to create a new one? Okay, so you see I've got one called One Mic Test here. Maybe that's the emergency template that I set up last time. In this case, I'm going to start one from scratch, and so I'm going to select blank project and choose create. So now that communication to the front end starts, and it figures out what kind of SCADAS I'm hooked up to, what kind of channels are available, and that sort of thing. And then I will be met with the software interface. Okay, and so you see the 12 channels of my access here. I've got my headset plus that SP-Diff input. I've got 7 channels of GPS, 2 tachos, and a CAN bus input. Okay, in this case, I'm going to make a very simple setup like I did last time. In this case, it's going to be one microphone, and it's going to be on channel 1. So one of the things that I like to do to make this whole process a little bit easier is just filter on this checkbox status. Okay, in this case, I've only got channel 1 turned on, so I just want to say show me all the trues, which is really only the one channel that's turned on. Okay, so my setup gets very much more simplified, and I'm just going to go step by step and set up like I did, similar fashion to what I did on the TestLab Scope app. In this case, I've got an ICP transducer. It's not just a voltage signal. And then I've got a point ID, and so I'll call this Mike. And this data rate field is, you see I have low, high, and slow. Slow would be something like a thermocouple that gets done very, very slowly. Where low and high is really just a default setting. Okay, I can say high, and then it will automatically set my sample rate to the maximum for the front end that I'm using, in this case 51.2 kilohertz. If I put this to low, I can still change this to 51.2 kilohertz. It's just going to default to what we kind of have as the default setting for low and high. So typically if you're measuring a mixture of accelerometers and microphones, you don't necessarily want to sample those the same because you're not usually interested in vibration data out in the frequency domain nearly as high as you are a microphone. Okay, so that's why we just call them low and high. In this case, I'm just going to maximize that out just like I did last time for the same reasons. I want to sample wide open. And then you see I've got a range. I've got my measurement quantity again, pressure, sensitivity. I don't know what the sensitivity of this mic is. I do know it's ICP, so I come down here and I can say read selected TEDs. It'll go out and read that, and it ports that sensitivity over for me. Okay, now I'm going to accept that TEDS measurement, and again this range, I'm going to leave this wide open. Okay, so this is something I didn't necessarily talk about on the Scope app setting, but on the SCADAS XS and on most of the SCADAS mobile cards, you have an adaptable range. Wide open, or the biggest range, is 10 volts, and that's where I would suggest we leave it for this super high flexibility test setup, because we don't want to have it set at 1 volt range and then end up overloading. Once we overload, our measurement is garbage, and so we never want to have an overload situation. So I'm going to leave the voltage range out as big as it can be, which is 10 volts. After the fact, if I make a measurement and I notice that the signals are all really, really low, I can always go in and edit these templates and adjust that range or add a auto ranging step to my process. But for right now, again, I'm making the most flexible, basic measurement template I can. I'm going to leave those ranges wide open. Okay. The next thing I want to do is I want to come down here to this measure tab, and this is going to be where I sort of set up those measurement start-stop criteria. Okay. In Neo, they all end up showing up over here in this controls parameters window, which will sort of dynamically change based on what I'm clicking on or what I'm looking at. And so in this case, I'm going to look under this measurement control, and you see this start trigger type is set to manual. I can have a stop trigger type as well. In this case, it could be a duration. I could say wait for a certain level on a channel. I could say take data for 30 seconds, etc. In this case, again, I'm going to leave it manual so that I am in full control, and I'm just going to start and stop. One of the other things I might take advantage of here is I might set this pre-start time. So I might set this to something small like 1 second and 1 second of post-stop. And what this is going to do is it's going to be buffering all of the signals coming into the front end, and then when I hit start, that's when the measurement will start, but it'll actually go back in time and bring with the recording that second that preceded me hitting that record button. Just in case I was late getting it started or something, this will ensure that I capture the entire event. Likewise, the post-stop will just say, here's the stop notification from the button. I'm going to tack on 1 extra second just to make sure I get everything. Maybe the structure's settling down, or who knows. Okay, those are there for your use. You don't have to use them, obviously, but might be nice. You can change the run name here if you're interested, but essentially I am ready to go. Okay, and so I'll show you what it looks like in TestLab Neo. So we have some pre-formatted live data displays for you. So you see the time display on the right, as well as the narrowband frequency spectrum on the left. So these are data that won't necessarily be saved. It's not processing this FFT in the recorded data that you'll get, but this gives you a live, during the test, monitor to sort of see what's going on. Okay, so it's a nice functionality built right into TestLab Neo. Okay, and so you see my whistle, and I get a live feedback of that frequency content. Okay, so that is setting up the measurement in TestLab Neo. Now, here's the critical thing. I want to go up and I want to say File, and I want to say Save as Template. So you see this check mark box right here, Save as Template. It tells you where it's going to put it in your user folder, TestLab version, project templates folder. We're going to call this Simple One Mic. Okay, and I save that, and I'm going to save it without any measured data because I don't have any, and even if I did, I wouldn't want that to be necessarily part of the template, so I'm going to save it. And now I'll exit TestLab, and I'll just go right back in, and I'll show you how easy it is to acquire data using that template. So I go into time data acquisition, boom, here in my recent, or I could favorite these. So if I favorited that, I could say show me only my favorite templates, Simple One Mic, boom, I'm creating a new test with that template. So it's got that microphone on channel 1, setting, recording that at wide open 51.2 kilohertz, and I'm ready to go. There's nothing else for me to do. Okay, so that is setting up a template in TestLab Neo. Lastly, I will show you the same setup in SimCenter TestLab, what we call Classic, which is the existing, long-standing SimCenter TestLab GUI. And the way I like to explain this is our signature product is called Signature, and so go to this TestLab Signature folder, and depending on the licenses or the tokens you have available, the most flexible way to do this is to start SimCenter Testing Advanced, because what this does is it brings with it the signature acquisition product plus time data recording. Okay, so that will nest them together. Let's say you don't have that many tokens and you just want to start signature acquisition. And this will be the basic product. We just want to have one extra step, which is certainly starting a new project here, but then we're going to want to go to Tools, Add-ins, and make sure we turn on Time Data Recording during signature testing, because that'll allow us to create the time data we're after. Okay, so I go up here to Tools, Add-ins, and I go down here, and it is already turned on because I used it last time I used signature acquisition, but this is going to allow me to record that throughput data which I'm after. Okay, very, very similar setup. It just looks a little bit different. Channel setup, very, very similar to what we did last time. The big differences are going to be in the tracking setup, and the acquisition setup tabs are where we're going to sort of determine our start and stop criteria, and then acquisition setup is where we're going to determine our frequency of sampling and things like that. So channel setup real quick, let me just put this into ICP mode. We'll call this mic. It's measuring pressure, and I'm just going to type this in for brevity's sake. So I've got one channel. Put it in the acoustic group just for fun, and I can see that acoustic mic ICP measuring pressure 45 millivolts per Pascal. Okay, and I'm going to head over to the tracking setup page, which will determine how my measurement starts and stops. In this case, I'm going to set up a time, and again, I'm going to put in some really big number, and the increment is where I will eventually get a calculated step. For time data, it doesn't even matter. Ultimately, all that matters is this tracked on time and this duration, which is a bunch of seconds. Now in acquisition setup, this is where I determine, or I tell the software what I want my sample frequency to be. This is all determined by this bandwidth, this top selection up here, which currently reads as bandwidth. And from your DSP, you should remember that bandwidth is 1/2 of our sample frequency in SimCenter TestLab. Now, we give you, so if I set this with a bandwidth of 25,600, that tells me that my sample frequency is being set in the background at 51.2 kilohertz, or twice this value, okay? Because I've got this set to display as bandwidth, because I want to know what's my frequency spectrum bandwidth going to be. If I want to change that, I can go to Tools, Options, and you see this General Options, this frequency setting. I can also say, always show me sample frequency. Okay, if I say OK, this will now update and it'll say sample frequency, and now it says 51.2 kilohertz. Okay, so it's just a matter of preference. We like to give you that option. I like to look at it in bandwidth. Other people like to look at it in sample frequency. Okay, so what this is saying is I've now turned on one mic. It's ICP 45 millivolts per Pascal. I said take data when I tell you to start, and go for basically forever until I stop you, and sample at 51.2 kilohertz. Okay, and then when I go to actually take data, I would go over to this measure screen. I would hit ARM. It didn't like that many seconds, so I'm just going to go 999. I'm going to arm this, and I'd be ready to take data. Okay, and when I'm ready to go, I hit start, and it's acquiring the data. It tells me it's measuring it. I take my data until I'm done, and I can hit stop. Okay, so this is no frills. You see there are no displays active or anything. This is just base how the software opens when you open it. You can certainly add a display and add some data there. I'll show you how to do that. And so I'll create a display here. I'll create a front back. I'll go over to this Data Explorer, and I'll grab some instantaneous acoustic data, and this will be the auto power of my microphone. I'll also create an additional display and I'll go to the monitor and I'll go time history. This will be the time of the mic. And so now I'll have two displays, and I see that time displays, the squiggly lines giving me the idea that there's data coming in. And on this tab, I also have what will start populating when I begin my measurement, the frequency spectrum. If I want to put a monitor in there, I would just do the spectrum of the mic like this. And now I see a live frequency spectrum like I did in Neo. Nice feature of Neo is it's already done there for you. But now I've got my real simple basic setup done. I'm going to disarm this, and I'm going to show you how to save this as a template in TestLab Classic. File, save as template, just like we did before, and I'm going to get a file. Again, I'm going to call this one simple mic, and I might call it classic here. And this will give me that .tpl file that I can then start a new measurement with. But one of the nice things that TestLab Classic does for you is it also gives you this option to create a template shortcut on the desktop. I always recommend people click this, particularly for these emergency situations. I'm going to create a template shortcut on my desktop. And now I'm going to exit this guy. I don't need any of this. And I'm going to show you what that template shortcut does. So you see this template shortcut it made right here, right on my desktop. Now if I double click this, you see it launches SimCenter. It's going to launch Signature Acquisition for me and automatically load that one mic template that we just made. So it is the easiest, fastest way to get a template going. You don't even have to remember what acquisition product you used. So you see one mic, and I'm all set. All right. So that is SimCenter TestLab time date acquisition in Classic. Okay, now we're going to talk about some simple frequency domain processing we might want to do in addition to just being able to take some time data. I'm going to show you some real simple processing we can do in SimCenter TestLab Classic, as well as our options for the same things in the SimCenter TestLab Scope app for the tablet. Okay. So first we need to remind everyone about the difference between a stationary event. Okay, so here our engine is idling or our cooling fan is running at a constant speed. Things aren't changing much over time, and we really want one sort of averaged frequency spectrum, one answer, if you will. And we have some options on how we want to do that averaging, but ultimately we want to end up with one plot like we see here. Okay, it's a frequency spectrum averaged over, say, 30 seconds. The opposite of that is a non-stationary event where maybe we're changing RPM or we're increasing the speed of our fan, and we want to see how the frequency content changes as that speed changes. Okay, so this is a non-stationary event. Here we need to figure out whether we want to track on maybe RPM or the speed of the fan, or maybe we just want to track on time. That's one of our choices, but we end up with a bunch of answers or a bunch of frequency spectra that we then put into a sort of three-dimensional plot like you see here. We call this a color map. And then we also have the options to decide how we want to track or display this versus time or RPM. So those are some real basic choices we need to make up front. First, we're going to talk about an average frequency spectrum using the SimCenter TestLab Scope app, which is on the wireless tablet with the SCADAS XS. Jump over to my screen share for my tablet, and I will start TestLab Scope. And of course, I still have my time data headset 1 microphone template there ready to rock, and so I can just go right to measure. And so you see it's right where I left off. We immediately are ready to take data if we want. Now, if I wanted to calculate an averaged frequency spectrum, I'm going to change this function that I'm looking at instead of being a sound pressure level versus time, I'm going to choose, in this case, I'll do an octave spectrum. And under this gear icon, I can change how this octave spectrum is calculated. Okay, so if I hit the gear icon, this is the FFT settings, and here we have the octave settings here. So you see it's A weighted. Right now it's not averaging, so it's like an instantaneous spectrum. If I click that, I can do a linear average, let's say. And again, I can specify an overlap. And what this is going to do is create an average spectrum for me now. And so now as I start talking, you see the spectrum is changing more slowly, right? And that's going to allow me to sort of calculate an average spectrum. So over the course of a quick measurement here, I'll show you how I can get this average frequency spectrum out of the SimCenter Test Lab Scope app software. So I'll start my measurement here. Okay, and I say stop. It does look like I overloaded a little bit, so I wouldn't want to do anything too important about this data, but for right now I'll just do a quick analyze. And in this case, so it looks like I overloaded the headset microphones. Those are closer to where I was clapping. So I'm going to analyze this microphone guy down here, and I'm going to go to the functions button, and in this case you see it's processing the data for each of the headsets and then my microphone, and I'm going to select this guy here. So now I'm looking at the microphone, and you see a time strip display down here, and you see the sort of double cursor. This is specifying the time over which I'm averaging the spectrum. Okay, so you see I took raw time data. Even though I was looking at an average with 50% overlap, I don't need to necessarily export that result. I could come in here and say only average, say, the whistling part, or I could grab this guy and say only average the clapping part, or the clapping plus the whistling, or I could just say average the whole thing. Okay, and so this is a way for me to specify very easily and graphically what content I want to include inside this average. Okay, and so let's say for whatever reason I want this whistle, but a couple of the impact events. All I have to do is come up here and I say export to, and I can save it right to an Excel file. Okay, so I export this and it's exported right to this XLS file, and I'll now be able to go import that XLS file, open it right up in Excel, and I'll have my plot. And I'll show you what that looks like here. Let me exit the full screen here, and I'll just go to my Xperia tablet, internal storage, go to DCIM, Siemens folder, exports, and here is my microphone. So this is the template name plus the date, and I will see my Excel data, which I can immediately plot as a 2D line. And of course I could format this and make it look a little bit prettier and put the x-axis on, but you get the idea. So that's how you can quickly export an average spectrum from SimCenter Test Lab Scope app. But now let's look at how we might do this from SimCenter Test Lab Classic. This is where we have our laptop hooked up to the SCADAS front end, and we want to set up an average spectrum. Okay, so again, I have my channel set up. It's our good old-fashioned simple one microphone setup. That hasn't changed. We're going to go to this tracking setup page, and here, instead of being tracked like we were before, we're going to choose stationary, and this is going to tell the software that we're going to average our results. And the simplest, easiest way to do this is to set the method to free run and then specify a number of averages, okay? And as well as this overlap percentage I like to use an overlap of maybe 50%. In addition, we're going to want to set the number of averages. In this case, let's say I just want to take 25 averages. Okay, so it's going to run and it's going to average 25 different averages, and each of those averages is going to be overlapped the previous one by about 50%. Okay, and you ask me, okay, Scott, how long are these averages? Well, we don't know yet because we haven't set up our acquisition parameters, and those we do on the next page. Okay, so I'm still going to say 25 averages, but how long is each average going to be? Well, that depends on this right here, my frequency resolution. So you see when my resolution is 12.5 hertz, in this case, I get a lot of updates per second on the screen. If I make this smaller and say 0.5 hertz resolution, now each average takes 2 seconds, or the inverse of this number. 1 over 1/2 is 2, and so each of these updates you see on the screen takes 2 seconds. Okay, so for 25 averages, it would be 2 times 25, about 50 seconds. Those are 50% overlap, so it'll be less than that, but just simple math here. So I need to keep that in mind. Ultimately, the length of my test is going to be determined not only by the number of averages, but how much time each average takes. I'm going to set my frequency resolution to 2 hertz, so 0.5 second for each average. Okay, and I'm going to do 25 of those, but they'll be 50% overlapped, and so it's going to take just a couple seconds for me to do this measurement. I'll go over to Measure Screen, and I will add some data here. So on the Data Explorer, I'm going to drop in, so the monitor in the front, I'm going to measure, or I'm going to display the instantaneous frequency spectrum of the mic, but then under the stationary in the back, I'm going to put the auto power, or the average of the mic, and we'll see how those two differ. So here are 25 averages, 2 hertz resolution. Okay, so you see the difference here. The red was the instantaneous, so average by average, that was updating. The green is the averaged result, and so you see how those two results differ. This is a nice way to look at data. So you see any contribution of an individual average as well as the average result. Okay, so I'll save that, I'll disarm, and then we can go look in the navigator at our average result here. So under section 1, stationary, I get an auto power of my mic, and that is my averaged frequency spectrum. I can also look at this obviously in a third octave spectrum just by using an octave display. Okay, so that's a stationary average using SimCenter TestLab Classic. How about a tracked frequency spectrum? Okay, so now we're going to have an event that is changing over time. And so we're going to go back to the software and we'll change how we set it up. So back here at tracking setup, I'm no longer going to choose stationary. I'm going to choose tracked. In this case, I'm just going to be using time to be my tracking method. I don't have an RPM or anything here. So I'm just going to take, let's say, 10 seconds of data, and this increment is how often do you want a frequency spectrum. Okay, so every 0.5 second, I'll do every 1/4 second, I'll do a frequency spectrum. So there'll be about 40 spectrums in my color map or my waterfall, 10 seconds for each second. Okay, and then acquisition setup. Again, each of them is going to take about a 0.5 second, so I'll have automatically built in about 50% overlap there. Each average is going to take about 0.5 second, and I'm going to create one every 1/4 second. Okay, so now I'm ready to take this data, and I'm going to remove this because I no longer have a average result, but I'm going to create a new display, this color map, and I will add time data, and I'll come in here and put the auto power of the mic, and we'll see that come in as the data starts beginning to come in, as the data starts streaming in. Okay? So here we go. Let's ready to do our test, and we'll start. Okay, so there is our frequency spectrum versus time. You get a quarter second, a half a hertz resolution for each frequency spectrum, and this is what it looks like. And I can say yes, and I'm afraid that's going to disappear. No, it won't. So I'll disarm here, and I'll go ahead and put this into decibels. It'll make it look a little bit more interesting. And so you see the whistle frequency changing with respect to time. You see my claps, which are sort of broadband in frequency. And I have this sort of nice tracked measurement. Real straightforward, simple. If I had an engine RPM or a rotating speed or a miles per hour speed channel that I wanted to add, very simple to add that. Just instead of tracked on time, I would select tracked on a channel in that tracking setup page. Okay? So now let's talk about how to do something simple like a sound pressure level versus time. Okay, so if I had a simple sound pressure level meter and I went out next to a highway or something, I could get a sound pressure level, overall level, a dBA or a dB value versus time. Let's see how I might set that up in TestLab. So back here, under tracking setup, I'm going to again track on time, and I'm going to reduce this to about, I'll leave it at a quarter second. Acquisition setup, I'll leave that the same. But now I'm going to have to use this online processing tab here. And I'm going to specify some different things. So you see I was automatically getting my auto power, my frequency spectrums, which could be either averaged or waterfall color map plots, because I had these set up. Now on this online processing, I'm going to specify an overall level, and I can do that here. And for acoustic channels, I can also create a second one with some weighting, in this case a weighting. But there's also, for specific to sound pressure level, there's also this level calculation where I can choose something universal, like a level, a weighted, a fast time constant. And I can add that and it'll calculate that. I can also choose the slow version, and I will get an LAF and an LAS. You see the time constant specified by the ISO standard there. And these will now be produced by TestLab automatically. So this will give me an idea of the overall sound pressure level versus time. Okay, so we'll go to measure. So now I'm going to take some new data, but I'm going to add a display here. So on this front back, I will add some of those new things that I just created. So time-based level. I'll do my LAF and my LAS, okay, as well as my overall level for my mic. Okay, so here we go. So you see the LAF and the LAS, obviously the time difference, the time constant difference has an effect on how the overall level is calculated, and overall level is even a little bit different. I could put this into decibels here, as well as the LAF, and you see all three give me a slightly different version of the overall level versus time, and it's all dependent on those settings, and use the one that you like best. Okay, now we're going to briefly go over how to set up a real simple resonant frequency test setup. So you've got some structure, an exhaust system, a steering column, some structure that you want to just do or maybe a repetitive survey, and I just need to know the first flexible mode or first resonant frequency of that structure. Real simple setup, but it will serve you very well if you set it up correctly, and you can go to it over and over and just get those measurements done real quickly. Okay, so the first thing I'm going to do is I'm going to jump out and go to Test Lab here under Structures Acquisition. I'm going to open a product called Impact Testing. Okay, it does just what it's called, or what the name would imply. We're going to impact our structure, measure the response, and then deduce from that what the resonant frequency is here. I'm going to start a brand new project. Okay, and I'm going to go to my channel setup, and by default it's got 2 channels turned on. So I'm going to make the first one my hammer. Always use your force reference on channel 1, and then my accel will be channel 2. These will both be ICP transducers, and I just generically say I'm going to hit in the down direction and measure in the up. And then under quantity, I'm going to measure force. I happen to know this is 2.25 millivolts per Newton. And my accelerometer, I can read TEDS. And so I'll insert that TED sensitivity. And my channels are ready to go. 1 channel force, 1 channel acceleration. I'm almost done. All I have to do is now go to this impact setup page, and I'm going to walk through these first 3 sub windows here. The first is called trigger, and this is going to set up my force channel or my hammer. So I'll turn on my demo view here, and I apologize for the sort of less than professional demo setup, but we're still in the home office and I don't do an incredible amount of impact testing in my home, so bear with the sort of janky setup. So I've got an impact hammer. I'm going to set up the trigger. So the trigger or the force on the hammer is going to be what starts the measurement or tells Test Lab I want to start taking data. So I'm going to first hit this Start Scope button here, and you'll see the data will start flowing in. And I'm just going to hit the structure a couple times how I plan on hitting it. Okay, so you see a couple averages hits, some small hits, some a little bit harder hits. It's going to take those, average them, and make some suggestions. Okay, so my current settings are shown here for input range, trigger level, and pre-trigger. I'm going to apply those suggestions, and I'm going to verify them once real quick just to make sure. And I did trigger, so I'm all set. My trigger is set. I stop my verify. I move on to bandwidth, and this is going to specify how big do I want my bandwidth and frequency to be. Okay, if I'm doing an exhaust system for an automotive application or a steering column, I don't need really beyond 100 hertz, and so I might change my sample frequency to be something 1024. So now this will get me a bandwidth out to about 500 hertz or so. That's going to be more than enough for most big heavy structures. In this case, I've got a really light little bar there, so I'm going to sample a lot higher in frequency because I don't know where the resonant frequencies are of this pry bar. So I'm going to start there, and I'm going to check my bandwidth, and this is really just making sure that my impact hammer, the tip, is stiff enough to get me out into the frequency range that I want before this force starts rolling off. Okay, so I see some resonant frequencies out here, certainly less than half of my applicable bandwidth, so I'm very comfortable that the tip I'm using is stiff enough that I'm putting a nice even amount of force in across the frequencies. Okay, so I'll stop there. Windowing, and this is going to make sure that my structure is no longer vibrating or still oscillating back and forth at the end of my time window, otherwise I'm going to suffer from leakage. And so I'm going to again start. It's going to tell me to take a measurement, and you see the unwindowed version up here. I'm going to stop even after one hit, and I'm going to apply those suggestions, and you see it's applying this force exponential window to make sure my structure is nice and died out by the end. Again, if you're working on a highly damped steering column or something, you're not going to have to worry about these structure or these settings. Your structure will die out. I'm using a very undamped metallic structure, and so I have to apply these things. And now I am ready to, again, say save as template, and I'll call this simple impact. Okay, and now next time I have an impact test come up, I can go and launch this template, and I will be able to take some data. So let's take a look and see what that will look like. In this case, I'm going to do 3 simple averages. It's going to tell me to go. I make my impact. That was a double hit, so I'm going to reject that one. And one more average for sake of argument. And I see some FRFs here. I could just look at those if I needed to, but in this case I'm going to go back to the navigator and I'm going to look under run 1. Here's my FRF, and I have a nice 3 average FRF, and I can add a single cursor and take a look and see where my first peak is, about 201 Hertz. So maybe that meets my design criteria, maybe it doesn't, but I have a very quick, easy way to look at my resonant frequency information. And if I created this plot as part of my template, it'd be all ready to go, and I could just drag and drop my data in. Okay, so that's how to do a quick and dirty, repeatable impact resonant frequency FRF. Okay, so that's the end of the presentation, but I wanted to take a minute and just talk a little bit about some of the things we can do with the time histories we've acquired using some of these quick setups. These are just a couple links from the SimCenter testing community. If you're not familiar with it, this is an online user forum and knowledge base where we post all kinds of articles on any number of topics. You can see some of the articles I just picked real quickly off the top of my head that deal with a little bit about how to process the time history data you've just learned how to acquire. So anything from calculating sound quality metrics to cutting orders and things like that. There's an article on here about the different averaging types. I just kind of breezed over that. You can look into that and see what all those different averaging types are about and that sort of thing. So I encourage you to go out there, poke around, and certainly my email is up here on the screen. Feel free to reach out. I really appreciate your attention and participation today. And yeah, reach out if you have any other questions. Thank you very much.